And now we move to the introduction of Professor John Church, who I will describe very briefly in the interest of time. John is going to speak to us about what do we really know about 20th and 21st century sea level change. All I'll say is he's a preeminent authority on the rate of sea level rise, a pioneer in the field, and we're honoured to have him present to us tonight as the winner of the 2022 James Cook Medal.
Thanks very much, Susan. And before I start, I'd like to acknowledge that tonight we're meeting on the land never ceded of the Gadigal people of the Aurora Nation, and pay respect to their elders past, present and emerging. So I should of course thank, I've got many collaborators, running out of time here tonight, so I'll just leave that list there and you can look at it. So an outline of today's talk. Let's see how this works. Right. This is very much my personal view of sea level science. I guess I've had a significant impact in that area. I'm going to talk a little bit about why it's an important issue, centennial sea level change through the 20th century, projections for the 21st century, and longer term implications, and finish off with a few conclusions. So we are clearly a coastal society. Our society has developed in a period of relatively stable sea levels and sea levels which were falling in many places around the world. And this has allowed our society to develop right up to the coast. And we're developing the land more rapidly with time. So this is a picture from the Gold Coast, just one example, where the population over 50 years, up to 2007, has increased by a factor of 10, and you can look many places around the world where that's happening. So if you want to look at the global numbers, 2.3% of the global area within 10 metres of current sea levels, called the low elevation coastal zone, but 10.9% of the world's population at densities of 240 people per kilometre. I won't go into these numbers here given the time, but perhaps something to remember. Today, roughly 230 million, or 2010, 230 million people lived within 1 metre of high tide level. So it's sort of a number to remember when you're thinking about what's happening this century. 2 metres, 400 million. By the time you get to 10 million, 10 metres, you're talking at over 1 billion people. So what causes sea level change? Well, firstly, there's the warming or cooling of the ocean, thermal expansion, exactly the same phenomena as you see in a thermometer. You warm the water, it expands, sea level rises. And this is one of the major contributions to both 20th and 21st century sea level rise. You can change the mass of the ocean by adding water to it from glaciers and ice sheets. This is called barostatic sea level, so changing the mass of the ocean. Or you can also change the mass of the ocean by changing the amount stored on land. So we've been building dams, reservoirs, which have been storing water, and we've also been extracting groundwater. Much of it eventually makes its way to the ocean. These are smaller terms, but they're important for understanding 20th century sea level change. And of course, what we're interested in is relative sea level change. So how's sea level changing relative to the coastline where we live? And that can change because of ocean circulation changes. So sea level rise is not uniform. Sea level rise, or sea level itself, is not uniform. We have ocean currents, and ocean currents change, changing the density distribution in the ocean, and this gives rise to a relative sea level change which varies across the globe. Just one point I want to make. So we measure relative sea level with tide gauges, but we also measure sea level with satellites. These are measured in different reference frames. Satellites measure sea level with respect to the centre of mass of the Earth, and if you want to compare these, you need to be careful about your reference frames. So I started in this business in the early 1990s when Graham Pearman gave a talk about climate change and sea level rise, and I thought he must have been wrong. So I started my own work, and on that basis I became an IPCC author, and through which process you learn a hell of a lot, having to read the extensive literature. So what did we know about the time I started? So we knew sea level was rising. Bruce Douglas made an estimate of about 1.8 millimetres per year, but with no acceleration in that rate during the 20th century. There was no accepted time series of global mean sea level which would allow us to try and dig into the causes of sea level change. We had observed trends in decadal variability in ocean heat content. For example, shown here are three different estimates, and they had this large variability with a peak in ocean thermal expansion, ocean heat content in the 1970s, and then a fall, and then a continued rise after that. None of the models that we had could simulate this. It was put down to being decadal variability, particularly in the North Pacific, but it was really an open question, I think. We had incomplete observations of ocean change, ocean mass changes, glacier mass loss, and little was known about the ice sheet contributions over the 20th century. So we had no adequate explanation of 20th century sea level rise, and that led Walter Munk, perhaps the most famous oceanographer, in 2002 to make this statement: thermal expansion and glacier mass loss cannot explain sea level rise in the presence of Earth rotational constraints, and we had no alternative explanation. He called this the sea level enigma. So that's changed quite a lot, and it's changed from global climate programs. People have taken a much more global perspective in recent times, and we've had much improved observations. So firstly, we have tide gauge observations, so they date from about 1700s, measuring coastal sea level. Recently, from 1993 on, we have satellite altimeter records. So these are really amazing satellites. They're measuring sea level virtually globally to a precision of about 1 or 2 centimetres. Work that I've been part of has actually looked at biases in this data, and we detected a small bias of the order of 1 millimetre per year in the first 6 years. But now we're talking about the accuracy of trends in this data being a couple of tenths of a millimetre per year. So this is really remarkable from a satellite that's 1,300 kilometres above the Earth's surface. We have much improved observations of the ocean now. Traditionally, these observations were made by ship, research ship, merchant ships, fishing vessels. But now we have these floats shown in the bottom picture called Argo floats, which sink to 2,000 metres in the ocean, drift for 10 days, rise up through the ocean, measuring temperature and salinity as they do that, transmit that data via satellite, then sink back down to 2,000 metres and repeat the cycle. And most recently, we have what's called the GRACE satellite mission. So these are 2 satellites following each other, measuring the distance between them, and that distance is affected by gravitational changes in the Earth. And so you can invert this data to estimate what gravitational changes there have been in different regions of the Earth. So the satellite altimeter record, this shows roughly 30 years of record from 1993 to 2023. Sea level rise is not uniform. The altimeter, because of its global coverage, really showed us how sea levels are varying around the globe. So over this period, there's a greater rise in the Western Pacific, the order of 5 millimetres per year, and lower rises in the Eastern Pacific, the order of 2 millimetres per year, and there's even a small spot in the Southern Ocean where sea level has been falling over this period. But this is a variable picture. Much of this variation we see here is natural climate variability, although there may also be an anthropogenic component to that. So one of our first results, we had a series of papers working out how do we estimate global sea level going backwards in time before the satellite altimeter. So we used the information from the spatial distribution from the satellite altimeter with the much longer record from coastal tide gauges to estimate how sea levels changed during the 20th century or back to 1870 in this diagram. So the rate of change, rate of rise is about 1.7 millimetres from this record, and we saw a clear increase in the rate, an acceleration in the rate of sea level rise. So when we first suggested this, we were called brave for making the measurement. I think people really meant stupid for making such a bold statement. But I think we've been fairly well proved right. That's now the accepted position. We have a very clear acceleration in the rate of sea level rise. And of course, this 20th century record compares with the pre-industrial record of the last couple of thousand years, when rates of sea level change have been the order of a few tenths of a millimetre per year at most. And as we'll see later, the current record, the most recent record from the satellite altimeter, shows a more than doubling of this rate of sea level rise. I was intrigued by what were these little bumps that we could see in the record from roughly 1960 on. And that actually led me to the cause of violent volcanic eruptions like this Mount Pinatubo eruption in the Philippines in 1991. So what that does is eject aerosols into the stratosphere at heights to the order of 20 kilometres, reflecting some of the sunlight. This is actually one of the basis for what some people propose as geoengineering as a way of countering anthropogenic climate change. And so you can actually see that in climate models. So these are 3 simulations in the 3 colours, blue, orange and green, of global ocean sea level and ocean heat content. And shown in the bottom 2 panels is the average of those, the difference between when you included volcanic forcing in the simulations versus not including volcanic forcing. And what you see after each of these volcanic forcings, particularly Mount Agung in 1962, 1963, El Chichon in 1982, and Pinatubo in 1991, a fall in ocean heat content with a gradual recovery over the subsequent 15, 20 plus years. I pointed earlier on to this unusual variability in the ocean heat content record, or the ocean thermal expansion record, shown by the yellow and red curves here. My colleagues, Susan Wafels and my postdoc at the time, Katia Dominguez, worked out that this was a bias in one set of instruments, a lower accuracy instrument, but one that was widely used around the globe. And when you removed that bias, you essentially removed this unexplainable heat content increase in the 1970s, and you ended up with the black curve. People have done a lot better than we did in 2008, but it's essentially the same record. And if you compare that record in the black curve, just look at the right-hand side. These are models with volcanic forcing. Then you see that the variability in a whole suite of models here, about 20 models, is similar to the observed record. The amplitude's not quite right, but it's somewhat similar, and you actually have an increased rate of ocean heat content and thermal expansion. So this was really quite a groundbreaking piece of work also. So the second major contribution to sea level rise is the loss of mass from glaciers. This is one of my favourite photos of glaciers, showing the Rhone Glacier in 1900 on the left and 2000 on the right. And you can see the dramatic reduction in volume of this glacier. The climate around that area has changed, much more trees growing up the slopes and in the valley. So clearly there's been a great loss of massive glaciers around the world, and in fact it turns out that they're probably the dominant term for 20th century sea level change. And so there's a whole series of people here, Graham Cogley, Hock, Radich, Mazayan, and others. Similarly, we've got much more improved knowledge about ice sheets, mainly in the satellite records, roughly from 1990 on, by, again, a whole group of glaciologists. And we have better information on terrestrial water storage. So Ben Chow, for example, estimated how much water was stored in man-made reservoirs, and Lenny Conoco and others estimated how much we were extracting from aquifers, which eventually made its way to the ocean. So now we actually do have a reasonable explanation for sea level change, and this is through a series of papers, and this is perhaps the most recent paper by Frederiksen et al. So in the top left-hand corner panel, the orange curve is an estimate of ocean thermal expansion during the period. The red curve is an estimate of the change in mass of the ocean, largely from glaciers, but with minor contributions from ice sheets in recent years and also changes in land water. And if you sum those two together, you get the black curve compared with the observational record in blue. So there's an approximate explanation for the observed sea level rise. So we've done this regionally as well as globally. And as I said before, sea level rise is not uniform around the globe. The top left-hand panel here is the amount of sea level signal you get from changing ocean circulation and warming of the upper part of the ocean. So you have a maximum in sea level rise at mid-latitudes, 30, 40 south in the southern hemisphere and 30, 40 north in the northern hemisphere. A minimum south of that in the Antarctic circumpolar current near Antarctica, and a maximum in the Arctic Ocean. But you also have other motions. The Earth is not solid, the Earth is always moving, so the top panel shows what's called glacial isostatic adjustment. So in the last ice ages, there were large masses of ice on the land. These depressed the land, forcing the mantle material out sideways and causing the land to rise surrounding the ice sheets, what was called the fall bulges around the large ice sheets in particularly North America and also Northern Europe and Asia. When you removed that ice, at the end of the last glacial maximum, that water flowed into the ocean. put more loading on the ocean floor and less on the land, and those four bulges have collapsed, resulting in greater than a global average sea level rise along the east and west coast of America, for example. And in the far field like Australia, because the land is sinking in the ocean floor, you actually have a slight sea level fall in the far field in places like Australia. So that's historical. It's an ongoing effect today and will be for many hundreds of years. But we also have an elastic response from changes in the current day ocean mass of glaciers or ice sheets. So in regions near glaciers, you're actually changing the gravitational field of the Earth. So the ocean is no longer attracted to those ice sheets or glaciers and flows away from them, and also the land rebounds because you have less loading on the land. So right near regions of mass loss, you have a sea level fall, and in the far field, in places like Australia, the Western Pacific, you have a larger than global average rise from the contributions from the glaciers and ice sheets. And you can look at the budget both globally and regionally, taking account of all these effects. And I've just picked out 4 locations here from a recent paper from a postdoc, Wang et al. Kanman on the east coast of China. The black is the observed record, and the red is the sum of all those different contributions. And they're approximately well explained by the observations, and the other curves there are the different contributions from glaciers, thermal expansion, terrestrial water storage, etc. Fremantle, on the west coast of Australia, large oscillations associated with the El Nino Southern Oscillation phenomena making its way through the Indonesian archipelago into the Indian Ocean. New York, sea level rising about twice the global average over the 20th century, primarily because of this glacial isostatic adjustment issue. And compared with Stockholm, where sea level has actually been falling, and this is in a region of former ice sheets, so the land has actually been rising. So when you put all of these processes together, you approximately explain the observed sea level rise. And we can, so that's based on observations alone. What about models? How well do the models do? This shows estimates of global average sea level rise through all the solid lines there, and the blue dotted line is what is now probably the most accepted estimate of historical sea level rise in approximate agreement with the record. There's quite a bit of uncertainty prior to about 2040, where the models don't fully explain the observed rise, but after 1970, there's good agreement between the models and the observations. And you can do that regionally. I won't, in the interest of time, I won't go through that, but we've looked at that at many locations around the world. So what about projections for the future? So these are the projections from the 6th assessment report, so just came out in 2021. Compared to sea levels in 1900. So for low emission scenarios consistent with the Paris Agreement, so that's a warming of about 1.5 degrees Celsius, then the sea level rise by 2100 is about 0.5 metre. At the other end, shown in the pink shading, is high emission scenarios, where sea level projections are about 75 centimetres by 2100. With the most extreme, there's a range of estimates going from about 60 to a little bit over 1 metre by 2100. And the dash curve I'll come back to, but this is a potential larger rise. So we've tried to evaluate those models through observations. This is somewhat difficult to do because there's only a small overlap between the observation period and the projection period. But this shows the satellite altimeter record from 93 to 2021 with an acceleration of 0.12 millimetres per year. When you look at the models and the historical sea level records from tide gauges, then you actually have quite good agreement in the trends in the period of overlap. And if you compare the accelerations over a historical period with the projected accelerations, what you find is that the observed acceleration is close to the upper end of what the models are saying. The uncertainties are large, though, because of this is a short period. You can also do regional distributions of sea level rise projected to 2100. On the left is the projections I was responsible in the fifth assessment report, and the right, the sixth assessment report. These are very similar, apart from two differences. One is a greater contribution from Antarctic to global mean sea level, and this actually means a smaller sea level change in that area of the West Antarctic ice sheet. And then there are these various highs in the regional distribution, which the AR6 ascribed to vertical land motion. These anthropogenic factors are not the only things affecting regional sea level, of course. Many cities, and perhaps the most well-known would be Jakarta, extracting groundwater from the surrounding regions. These are causing those sediments to compact. They compact naturally in estuarine delta areas anyway. The numbers can be large, and as you know, Jakarta, Indonesia is changing its capital city from Jakarta to a new location because of this problem. What about the longer term? Well, we can look back at the historical records or the paleo records. So this is a paper from 2015. So current day CO2 concentrations have gone from about 280 parts per million in pre-industrial up to today they're about 414 or so parts per million, continuing to rise, and a warming of about 1.2 degrees Celsius up to today's value. The last interglacial period, so that's roughly 125,000 years ago, sea level was higher, so this estimate is 6 to 9 metres. I typically think of it as 5 to 10 metres, at temperatures similar to today's compared to pre-industrial, but at lower CO2 values. So these numbers are being revised. The latest estimate, which I have a lot of sympathy for, are about half of this 5 to 10 metres of sea level rise in the last interglacial. And if you go back to 3 million years ago in the mid-Pliocene warm period, then sea level was quite a bit higher at CO2 concentrations roughly similar to what we have today. So I think this gives a clear indication that sea levels are out of balance with the current climate, and we are in for further rises into the future. Again, there's been revised estimates of this mid-Pliocene warm period sea levels, and because some models are tuned to these paleo records, then they are somewhat sensitive. So longer term, where can the sea level contributions come from? Glaciers only have a limited amount of mass in them, the equivalent of about 0.4 metres of sea level rise. Ocean thermal expansion will continue for centuries at the rate of 0.2 to 0.6 metres per degree Celsius. Greenland is, I think, a major concern. It has enough water in it to raise sea level by about 7.4 metres if it all melted. There's two different scenarios that are proposed at this stage. One is a threshold. So what happens is as the Earth warms, you increase the amount of melt from the Greenland ice sheet, but you also increase the amount of precipitation on the Greenland ice sheet. But increased melting wins, and there's a threshold above which the ice sheet would inevitably decay. An alternative proposal put forward by my colleague Jonathan Gregory is that it's not so much a threshold, but there is quite a sensitivity such that for greater than 2 degrees Celsius, you're talking about 4 metres of sea level rise. Both of these phenomena, both of these processes are relatively slow, so you're talking about over 1,000 metres, 7 metres over about 1,000 years. Antarctica is what's created most concern, I guess. There's 55 metres of water at sea level in Antarctica, 5 metres in the West Antarctic ice sheet, and there the issue is that the ice sheet is grounded on rock that is below sea level and gets deeper as you go back from the coastline. You can have warm water penetrating underneath the ice shelves, melting them at the base and allowing that grounding line to retreat. Once it retreats into water or into land where the ice depth is getting deeper as you go landward, that's potentially unstable. It leads to a larger flow, more rapid flow of ice into the ocean and further retreat of the ice shelf. So this is a process called marine ice sheet instability. It's approximately included in current day models, but some people would say we don't resolve the features adequately to actually see the rapid response that we might expect. There is a second process which is very controversial, which is that the ice shelves decay. We know the ice shelves decay. We've seen that happen on the Antarctic Peninsula, where an ice shelf decayed in months, and that led to a more rapid flow of ice into the ocean from the glaciers behind that ice shelf. But on the main parts of Antarctica away from the peninsula, people haven't seen this marine ice cliff instability. And what it is, you have the shelf decay, and once the edge of the ice sheet is greater than some depth, some height, like about 100 metres, then the ice sheet can start collapsing on its own. And people have, there's one set of models run by DeConto and Pollard which incorporate this process. They argue that it's necessary to simulate the historical sea levels, and that leads to a much more rapid and larger sea level rise. But it's very controversial, and not everybody agrees with it. Okay, so we estimated in the previous report that there's only medium confidence that any additional contribution from marine ice sheet instability could contribute significantly to 20th century sea level rise, and that would be up to several tenths of a metre. And it's potentially actually already occurring in some regions. We don't have good descriptions of that, but there's some potential that we've actually already triggered this, as we might have already crossed a threshold for the Greenland ice sheet. If you take this marine ice cliff instability and tune it to the historical sea levels, then the DeConto and Pollard estimate is given in blue. So if we just look at 2300, you're talking at sea level rise of the order of 10 metres. That's a very rapid rate of rise. That would challenge what we've seen historically. If you use the new estimates of the paleo sea level, then you get the yellow, the pinkish sort of colours. At most half the rate of decontinent pollard. But this is reason for concern. And of course, sea level impacts will be felt most acutely through extreme events. For example, this example of in the northern suburbs of Sydney, and these extreme events occur through a combination of tides, storm surges, waves, seasonal and interannual variability, and of course sea level rise. And this rise can change what is currently a 1 in 100 year event today into something that might be occurring annually or more frequently than annually by 2100. So we will need to adapt. We cannot stop all sea level rise, but we do need to urgently mitigate if we are to avoid the worst case scenarios. So how can we adapt? We can retreat from the coastline. It's already happening in parts of the world. We can accommodate rising sea levels. So the second picture is an example of storm surge shelters in Bangladesh, which have saved many tens of thousands of lives, where people can retreat to these shelters, which are used as schools at other times during storm surges. Or we can protect parts of the coastline, and we're doing that also. So the Thames Barrier protects a huge quantity of infrastructure behind that, and similarly barriers in Rotterdam. So where are we now? Our current warming is about 1.2. I'll be interested to see what this year will be. It almost certainly will be a record warm year again. So perhaps 1.3 degrees Celsius. The Paris Agreement has a target of 1.5, so we're almost there. Current policies and actions lead to about a 2.7 degrees warming, with quite a bit of uncertainty, of course. Actual targets, people are actually saying that they will do better than the current policies indicate, and that would suggest 2.4 degrees Celsius. If you take the targets and the pledges that people are making about becoming carbon neutral, you're talking about the order of 2 degrees Celsius, and only with a very optimistic scenario would you get to below 2 degrees Celsius. So this is above what we would hope for with the Paris targets. I'll just put up a quick summary. Today's society is potentially vulnerable to rising sea levels. Historically, in warmer climates, sea level was higher. Sea levels are currently rising at an accelerating rate. The current understanding gives us some confidence in our ability to project sea level rise into the future, but there's really major questions about the contribution of the ice sheets, both the Greenland ice sheet and particularly the Antarctic ice sheet, and their dynamic response. The significant uncertainties about this. Avoiding crossing thresholds leading to metres of sea level rise and hundreds of millions of people being impacted requires urgent, significant and sustained mitigation. But we can't eliminate all risks from sea level rise. We will need to adapt as well as mitigate. And of course sea level will be felt most acutely and first through the impact of extreme events. So I should stop there. Thank you.
Thank you very much, Professor Church. I may start with the greedy first question. So if we do actually get a tackle on the temperature rise, given the amount of energy this water takes, it's actually going to take a bit of time for that to stable, isn't it? And any volcanic or reduction, there's going to be a degree of, and this may be decades or longer, would be a reasonable statement?
Absolutely right. So the ocean at the moment absorbs about 90% of the increased energy in the climate system from anthropogenic climate change. Compared with the atmosphere, contains about 1%. So almost all of the energy is being stored in the ocean. The oceans and the ice sheets are out of balance with the current climate system. The oceans will continue to warm for centuries. Ice sheets will continue to respond on that sort of timescale as well. So we're talking about sea level rise continuing to rise for centuries, even after we've stabilised surface temperatures. So this is a long-term impact which we need to think about.
Thank you.
Thank you for your presentation. I was intrigued with the photo, actually, of the Northern Beaches damage. I studied coastal engineering about 50, 60 years ago, and Professor Doug Foster predicted that 60 years ago. It had nothing to do with sea levels. It had all to do with council planning and littoral drift along the coast. So I was reminded when I saw the photo, I said, well, yeah, I mean, we knew that 60 years ago, so that's got nothing to do with what we're talking about here. But I was intrigued, you didn't mention at all evaporation and changing weather patterns and the movement of water from the ocean via evaporation. I would have thought that was quite significant. Even in my swimming pool, I can see evaporation over a period of months is quite significant, actually more than what you're talking about here in that period of time. Why isn't evaporation and weather patterns studied in this?
So weather patterns are part of this. So the regional distribution of sea level, which I showed in the ocean dynamic response, that's part of that response to changing weather patterns. And so the example I showed was higher than global average sea levels at about 30 degrees north and south, 30 to 40 degrees north and south, and that's associated with change in weather patterns. And yes, evaporation increases, the ability of the atmosphere to transport water vapour increases. It goes up about 7% per degree Celsius, and that's an important component of climate models, so that is addressed.
Excuse my ignorance on this. When the ice sheets melt, for example, you've given the talk of Stockholm, that example of Stockholm where the ice sheet melts and the rocks actually rise. I can imagine it must be a very complex matrix of all sorts of things happening underneath the surface to make those rocks rise. Can you help me understand what that would be, what that picture would be, just simply?
So the process is that during the last ice age, there were large ice sheets over Sweden, Norway, etc. And that pushed the land down. And the mantle material underneath that ice sheet flowed out to the surrounding regions. When you removed the ice sheets, the land started to rebound and the mantle material started to flow back to where it was previously. Think of squeezing a tennis ball. When you squeeze it, that's the ice sheet compressing it. And it flows out to change its shape. When you release your pressure on that tennis ball, the land's rebounding. And that's what we're seeing in Norway and Sweden. And it's just the opposite in places like New York, which were in the forebulge region, immediately adjacent to where the ice sheets were. And there the mantle material is flowing back to where it had previously been under the Northern American ice sheets. So I'm not sure that's explained it at all.
It has. The mantle itself, I'm imagining that to this all. What is it made of? Is it rock? Is it sediments? What is it?
It's like you're pushing my knowledge here. It's like a viscous material, something like tar, I suppose. So it flows, but it only flows very slowly. And that's why you're seeing this ongoing response.
Thank you, John, for your talk. Pardon me. I've so few questions and meetings recently, I'm losing my voice. You referred occasionally to geological influences, and I wonder whether the effect of global tectonics, the big movements that are occurring in Earth's crust and so on, are taken into account sufficiently. And my own experience working around Papua New Guinea in the old RV Franklin was that we saw on the Huon Peninsula, for example, in PNG, coral reefs many hundreds of metres above sea level today, young coral reefs basically, geologically. And not far from there, we would see seamounts, volcanic seamounts on the seafloor that had sunk since they were formed, probably under their own weight, because you could see that the surrounding sediments had been bowed down around the volcanic centre, and on the crest of those seamounts, which were about 400 metres, 600 metres below sea level now, there were modern coral reefs. So they're in the same part of the world, but different geological provinces. We've had huge rises of the land relative to sea level and huge falls of the land relative to sea level. These sort of things are probably not been measured or observed all around the world, particularly around the Pacific, the so-called Rim of Fire. But they're probably, the PNG is probably representative of a lot of the oceans, the oceans surrounding PNG are probably representative of a lot of the oceans. Do you think that we have an adequate understanding of the effects of tectonics on sea level rise?
So there's a number of different issues. So people like Kurt Lembeck use those historical estimates of sea level change to develop models of GIA, Global Isostatic Adjustment. But there's also the longer term issues, which is part of what I think you're referring to, which are to do with the dynamic response of the mantle. How is the mantle changing, and how is that changing the Earth's surface? And that's what's behind these recent reanalysis of the mid-Pliocene warm period in particular, that how do we get a handle on what that dynamic response of or the dynamic nature of the mantle has been, and how has that changed sea level? So this is relatively recently been addressed, but it's recent. There hasn't been a huge amount done, but people are trying to address that. There's also, of course, lots of other type tectonic motions, so volcanic issues, earthquakes, etc. So yeah, there's lots occurring in the movement of the Earth, and some of it's better known than others. So there's work to be done.
I think that may be the questions. Okay. Well, my apologies. I've got confused on who was doing the thanks this evening. I would like to, on behalf of the Society, pay a very, very well-wished thanks for the presentation, and it was very great information and a very enjoyable presentation.